Hello students, welcome to Engineers Academy. I hope you all guys are doing good. If you are here for the first time, do subscribe Engineers Academy. That will help to promote my channel and will help to reach out many more students like you guys. Now we are going to solve this problem from Vector Mechanics for Engineers by Baer and Johnston, chapter 3. The problem says that ropes AB and BC are two of the ropes used to support a tent. So we have these two ropes AB and BC. There are several ropes which are used to support this tent, but in the diagram we are shown these two ropes. So it is said that the two ropes are attached to a stake at B. So we have the stake at B like this. If the tension in rope AB is 540 Newton, determine the angle between rope AB and the stake, and B, the projection on the stake of the force exerted by the rope AB at point B. So in part A, we are asked to find the angle between this rope AB and the stake. So if we represent that rope here, this is the stake, so we are required to find this angle theta between the rope AB and the stake. So as we have learned and we have discussed that we can find the angle between any two vectors by using the dot product. So there are several equations you guys can use to find the angle, but in this particular problem we are given the tension in the rope, so we can use the dot product of the tension in rope AB. We can say TAB vector dot product with, since we want to find the angle between this rope and the stake, so if we take the dot product of this tension vector with the unit vector along the stake, so the unit vector along the stake is this lambda BD, so this will be equal to, since the dot product of any two vectors gives us the projection of one of the two vectors onto another one. So if we take the dot product of TAB with the unit vector along the stake, this will give us the projection of this AB tension along BD, and the dot product always gives us TAB. This will give us TAB cos of theta. So TAB cos of theta, this is basically the projection of the tension along AB onto the stake. So we can say that the projection of AB, or we can say that the magnitude of the projection of AB along the stake BD is equal to the dot product with the dot product of TAB with the unit vector along BD, and this is further we know that this will be equal to TAB cos of theta. If we know the angle between the stake, if let's say if this is the stake, this is BD, and somehow the rope is like this, so this is, let's say, that point A. So the projection of the tension along AB, so let's say this is the TAB tension, this is TAB. So the projection of this tension along BD, let's say that this is 90 degree, let's say. So then this will be, if we draw another vector along BD, so this blue vector, if this is the angle theta, then this blue vector is the projection of that TAB along BD, and this projection will have, if we look into this if we look into this triangle from this side, and if this is a right angle triangle, then we know that this particular projection is the component of TAB, and this will be the cos component. So we can say that the projection of this TAB along BD is equal to TAB cos of theta. So now in this problem we are asked to find the angle between the rope AB and the stake, and the projection on the stake of the force exerted by rope AB. So this, if we somehow find this dot product, or if we find TAB, if we find somehow angle theta, and we are given the magnitude of TAB, the magnitude of TAB is 540. So if we somehow find the angle theta and then multiply, take the cos of theta, the product of this TAB with cos of theta, we will be able to find the projection. So this will be the answer for the second part. But for the first part, we can use this equation and we can find TAB Cartesian vector. We must find the unit vector along the stake, and then dividing this dot product by the magnitude of TAB and taking the cos inverse will give us the angle theta. Now, as we have discussed in the previous videos, that we can always find the angle between any two vectors by using the dot product of the position vectors. So if we take the position vector from B to A, and if we take the position vector along the stake, and if we take the dot product, that will give us the angle at B as well. So we can say that R of BA, position vector from B to A, dot product with the position vector from B to D, this will be equal to RBA magnitude, RBD magnitude, and cos of the included angle. So we can say, if we rearrange this, then cos of theta is equal to RBA dot product with RBD divided by RBA magnitude, RBD magnitude. And if we look for this equation, then this divided by this, the position vector by its magnitude is the unit vector. So we can always say that this will be the unit vector from B to A, and dot product with the unit vector from B to D. So if we take the dot products of the unit vectors and take the cos inverse of that, we can also find the angle theta. So either you guys can use this equation to find angle theta, either you guys can use this equation to find angle theta, or either you guys can use this equation. So all of these equations are almost the same equations. So you guys must know that since we want to find the angle at B, so then we must take the dot product of TBA with this, right? So let me modify this. This will be TBA. Remember, this is TBA, and similarly this will be TBA, and similarly here we will have TBA as well, right? So this will be TBA, and this will be TBA as well, and this is TBA as well. So now let's use this equation 1, and we will be able to find the theta angle, right? So for that we have to find the Cartesian vector representation of the tension from B to A. So we can say that TBA vector, this will be equal to TBA magnitude, which is 540 Newton. This is given in the problem statement, multiply by the unit vector from B to A, and again we know that this is 540, and the unit vector from B to A is the position vector from B to A divided by the magnitude of the position vector from B to A. So for this we have to find the position vector from B to A. So let's find the position vector from B to A. So the position vector from B to A. So again what we need to do is that we need to travel from B along the x, y, and z directions to reach that point A. So from B we need to travel this distance, and this distance is traveled in the negative z. This distance is 1.5. So in the negative z, or in the negative k, we need to travel 1.5 meters. So we can say 1.5 in the negative k. So we have reached here. Then from here we need to travel this distance. So this distance is in the negative x. So in the negative I, we need to travel 3 meters. So minus 3 I. And then from here we need to travel 3 meters in the positive y direction. So 3 meters in the positive j. So plus 3j. And now we can find its magnitude. So its magnitude is, we can say this will be 3 square plus 3 square plus 1.5 square. So this gives me 4.5. So this is equal to 4.5. And since these are in meters, the unit of this position vectors is in meters. This is in meters and this is in meters. So the direct distance between point B and A, or we can say that the length of the rope from B to A is 4.5 meters. The magnitude of the position vector always gives us the direct distance between the 2 points for which we are finding the position vector. So now we know the position vector from B to A and its magnitude. We can plug in here, so we will be able to find TBA. So TBA is equal to 540 and multiply by the unit vector. So we can say that this is minus 3I plus 3J minus 1.5K divided by its magnitude, which is 4.5. So 540 divided by 4.5, 540 divided by 4.5, this is 120. So we can say this is 120 or if I multiply this 120 inside, so this is 120 into 3, which is 360. So this is 360I and minus plus 360J, and 120 into 1.5, this gives me 180. So minus 180. Okay, so this is the tension in rope BA from B to A. So this is the Cartesian vector representation of the tension in that rope from B to A. And now we have to find, to use this equation, we have to find the unit vector from B to D. So the unit vector from B to D, we can say that the unit vector from B to D, this is equal to the position vector from B to D divided by its magnitude. So now the position vector from B to D will be from B to D like this, right? So we are given extra details here, so we will be using the position vector from B to D here, and again using the same method we will try to reach that point B while traveling from B in the direction of x, y and z in any order, right? So now to write the position vector from B to D, let me write that this unit vector from B to D. So from B we need to travel this distance. So remember that this is our positive z direction, this is our positive x, and this is our positive y. So let me represent that. From B we need to travel 0.16 meters in the positive z direction. So in the positive k we need to travel 0.16. So we will reach here. Then from here we need to travel 0.08 meters in the negative x. So in the negative I, 0.08, and then in the positive y direction 0.38 meters. So in the positive j, and this is I, 0.38 in the positive j, and this is in the positive k. And now the magnitude will be 0.08 square plus 0.38 square, 0.16 square under the square root. The unit vector from B to D is this is equal to 0.42, and we can divide each and every component by 0.42. So we can say that this is equal to minus 0.08 divided by 0.42I plus 0.38 divided by 0.42J plus 0.16 divided by 0.42. Okay, 0.08 divided by 0.42, this gives me 4 divided by 21. So this is equal to minus 4 divided by 21I. Then 0.38 divided by 0.42, this gives me 19 divided by 21J. And then we have 0.16 divided by 0.42, this gives me 8 divided by 21. So plus 8 divided by 21k. So this is the unit vector along the stake from B to D. Now using equation 1, we can find the angle. So this is our equation 1, and we can say that TBA cos of theta is, or we can say that cos of theta, or let's say this is TBA cos of theta is equal to TBA vector dot product with the unit vector from B to D. So now TBA vector is this one, this is TBA vector, or we can say this is TBA vector. Now it's up to you guys. I'm going to use this one. So TBA, this is my TBA vector, so we can use it here, dot product with this, which is minus 4 divided by 21i plus 19 divided by 21j plus 8 divided by 21k, or we will write it as TBA cos of theta. Now we can multiply I with I, j with j, and k with k. So minus 360 into minus 4 divided by 21. So minus 360 multiplied by minus 4 divided by 21. This gives me 68.571, or we can say it is 480 divided by 7. So we can say 480 divided by 7, and I dot I is 1. Similarly, 360 into this, 360 into 19 divided by 21. So 360 into 19 divided by 21, this gives me 2280 divided by 7. So plus, we can say plus 2280 divided by 7, and this minus 180 into this. So minus 180 into 8 divided by 21. This gives me minus 480 divided by 7. So minus 480 divided by 7. So as you guys can see, this will cancel out with this one, and we are left with 2280 divided by 7. So TBA magnitude is given. So TBA magnitude is 540 Newton in the problem statement. So we can say that cos of theta is equal to 2280 divided by 7 divided by 540. So we can say that 2280 divided by 7 divided by 540. So this gives us 0.603, or we can say 38 divided by 63. So let me write it in fraction. 38 divided by 63, and if we take cos inverse, then theta is equal to cos inverse of 38 divided by 63. So we can say that cos inverse of our answer is the angle, right? So theta is equal to 52.90. 52.902 approximately. So now the angle between the rope from B to A and the stake, this angle is how much? It is 52.902. Now if you were not given the magnitude of the tension along BA, we can always use the position vector. We can always use this formula. If you guys use the position vector from B to A, the position vector from B to D, and their magnitudes, you guys can always find the angle theta. So I will leave this particular concept to you guys. Use this formula and find the angle theta, and let me know in the comments if you got the same angle theta from this formula or not. Now in the second part, we need to find the projection on the stake of the force exerted by rope AB. So we want to find the projection of the tension along BA onto the stake. So as we know that this is the projection, this projection from of the tension from B to A onto BD is equal to this TBA cos of theta. So since we know the angle now, we can say that for part B, the projection of the tension from B to A on the stake BD is equal to TBA magnitude cos of theta. Now we know TBA magnitude, which is given 540, and we know theta as well, or we know cos of theta as well. This cos of theta is equal to this. So 38 divided by 63. So 540 into 38 divided by 63, this is cos of theta, will give us the projection. So 540 multiplied by 38 divided by 63, this gives us 325.71, and this will be in newtons since 540 is in newtons. So the projection of the tension along the stake is 325.71 newtons. So what does the projection mean? That out of 540 newton, 325.71 newton force is acting along the direction of the stake. So this is the solution of this particular problem. I hope this will help you in your learning. Do subscribe Engineers Academy for the solution of such more problems from Vector Mechanics for Engineers by Bear and Johnston.